In this video, I want to go over a few details about exponential functions that I didn't cover in class today. So exponential functions are of the following form. So we can have exponential growth, and these are cases where the function is growing. So we might have p of t equals p naught a to the t. And in this case, a is greater than 1. So in the chocolate example from class, a was 2. And we also have exponential decay. And the formula for that is the same. It's p naught a to the t. But in this case, a is less than 1. So the smoke particles from the tofu fire that get filtered out of the air, that example from class, a was 0.6. So same formula in both cases. For growth, a is greater than 1, and for decay, a is less than 1. Now, there's another way that exponential functions are very often written, and that's as follows. So we could also write p of t equals p naught e to the k t. So they're often written using an exponent to the base e, where e is a special number 2.78, blah, 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 blah. So for reasons that I can't explain now, but we will be able to talk about in Chapter 2 or 3 of this course, e is this very special number that has these magical properties. For now, it should seem like a very perverse number, or certainly not a special number, and it should be mysterious as to why people are fixated on using this for exponents. So let me see. So for exponential growth, we can write it this way or we can write it this way. These formulas look different. Well, the p naught, that's our initial amount of chocolate, that's the same. But the formulas, or the functions, are exactly the same. They're written differently, but they stand for exactly the same thing. If you plug in t of 1, 2, 3, whatever it is, you'll get the exact same number. So these are sort of like having the exact same thing described in two different languages. The words or the sentence might look different, but the underlying thing is exactly the same. If we have exponential growth, then k is greater than 0. Well, actually, let me write it this way. In all cases, k will be greater than 0. If we have exponential decay, p naught is e to the minus kt. So for exponential growth, we have e to the positive something. Exponential decay, we have e to the negative something. And what's this quantity k? Well, k is known as the continuous growth rate. So k is the continuous growth rate, and we'll be able to justify maybe in 4 or 5 weeks why k is called the continuous growth rate. For now, the stuff over here should be a little bit mysterious, but hopefully not too unsettling. You might need to do a little bit of this and just sort of know this terminology and these algebraic forms for the homework for this week. Later, I think in Chapter 1-4, we'll learn how to go from this form to this form and back. So we'll learn how to do this translation, and then you'll see, maybe more directly, that these two forms really are the same. But for now, the main thing to know is we can have exponential growth, exponential decay. For exponential growth, we have a positive a, or a greater than 1. Exponential decay, a less than 1. And if we write it in this continuous form using the base e, which is this funny number, if it's e to the plus k, whatever, t, then it's exponential growth. And if it's e to the minus kt, then it's exponential decay, like the smoke particles, and k is known as the continuous growth rate.